In the previous MindBite, we looked at the mathematics of AM modulation. We saw that an AM modulated signal could be formed by multiplying a baseband information signal by a carrier wave. In this MindBite, we look at the hardware of how that's actually achieved. We also look at demodulation, the process of extracting a baseband signal from a modulated signal. So we look at super heterodyne modulation. This is the most standard way of implementing the multiplication by a carrier wave to produce a modulated signal. Then we look at two different methods for demodulation. One very similar to super heterodyne modulation, and the second a non-coherent method called envelope detection. So just to remind you what an amplitude modulated signal looks like. It comes in a product of two terms. Here we have the carrier wave term, and here we have the message signal term, shifted and scaled to avoid crossover distortion. And this plot is what a typical amplitude modulated signal looks like. It has a high frequency oscillation at the carrier frequency, and the amplitude is modulated by a message signal. Now we know that modulation moves information from one frequency to another, and so it must use non-linear circuit elements to achieve that. This is because linear circuit elements will not move information one frequency to another, so no network of resistors, capacitors or inductors will do the job for us. So we need a non-linear circuit element. This is the characteristic of a diode, which is non-linear because of this angle here. And in general, a non-linear circuit element can have a characteristic performance, i.e. voltage in divided by current flowing through it, which has any arbitrary curly shape. Now normally, a hardware multiplier is a special form of general nonlinear system. So if you imagine a hardware multiplier exists, this is a piece of hardware with two inputs. In one input we'll put a carrier wave, and in the second input we'll put our message signal. Now in the slides that follow I represent the message signal as a pure tone at the message angular velocity. But if these systems work for one tone, then they'll work for a baseband signal simply by adding them together. If you multiply two cosine terms together, then the output can be written as a sum of two cosines, one at the difference frequency and one at the sum frequency. For transmitters, we usually want this element because this is at the higher frequency. And at receivers, where we want to demodulate, we want the lower frequency, so we want this term. So a transmitter will filter out the low frequency term, and a receiver will filter out the high frequency term. These multipliers are general nonlinear pieces of hardware, and they've been engineered so the output is dominated by the product of the two inputs. But all other terms will be in the output as well, such as the input carrier wave, a small amount of that will go straight through. The message signal, some of that will go straight through. Also the carrier squared and the message squared, and all powers and products of the two will appear at the output. Now the hardware multiplier has been engineered so the major part of the output is the product of these two signals, but all the other combinations will be there, and generally these have to be removed by filtering. So this is the block structure of a general transmitter. You have a hardware multiplier which modulates up an input message signal by multiplying with a carrier wave at an intermediate frequency. That's what the IF stands for. Now at this output you have the baseband signal modulated up by amount given by the intermediate frequency. There's all the other junk terms produced by the multiplier as well, and the high-pass filter will remove a lot of those. Now this intermediate frequency is chosen so that all the filtering that goes on in here can be achieved with normal resistors and capacitor type components. So you choose the intermediate frequency to be convenient to you. Then the signal is upshifted again by multiplying by a oscillation at the difference between the carrier and the intermediate frequency. And so this upshifts from the intermediate frequency to the transmit frequency. Now there's also going to be a term at the difference between intermediate and carrier, i.e. at a much lower frequency, and that's removed by high-pass filtering. And this will go on to some sort of antenna. So why do we upshift in these two steps? Well, there's several reasons. Firstly, this part of the transmitter is working at very high frequencies, hundreds of megahertz or a gigahertz. And so these components, the multiplier and the oscillator and the filters, are all quite expensive. These filters will not be resistors and capacitors. It could be materials which allow only some frequencies through. This part of the circuit is much easier. It's working around the intermediate frequency, which we've chosen to be convenient to us so we can buy cheap components. Also, it's normal to have several of these parts of the circuit so you can combine several signals at the intermediate frequency stage and then upshift all of them to the transmit carrier frequency. Lastly, these oscillators will have an error, i.e. they'll produce some harmonics, and so it's cheaper and more stable to upshift in two stages using lower frequency oscillators than doing the whole lot in a single stage. So demodulation is what happens at a receiver. It recovers the low frequency information from the signal from the high frequency modulated signal it receives. Now it's just the same as modulation, it's shifting information between frequencies, and so the same sort of non-linear devices are needed, and because of the junk these things produce, you'll also need some filters. There are two different types of demodulation we'll be considering. There's the coherent demodulation, where the receiver has an oscillator that's locked to that at the transmitter. Now, for communications to be needed, the transmitter and the receiver must be some distance apart, so it's not easy to have an oscillator that's locked to one which is some distance away. The other sort of demodulator is called a non-coherent demodulator, and it does not need a locked oscillator. So the second sort tends to be expensive but good, and the first sort is cheaper but not quite as good in terms of performance. So here we have a typical coherent demodulator based on the same super heterodyne multiplication process that we saw in the modulator earlier. At the input we have our modulated signal, which is our message signal that's been upshifted by our carrier frequency. When we mix that with our carrier frequency, at the output we have two components. We have an oscillation at the sum frequency, which is at the message frequency plus twice the carrier frequency, and we also have an oscillation at the difference, which is at the message signal plus the carrier frequency minus the carrier frequency, i.e. at the message frequency. So the low-pass filter gets rid of the stuff at twice the carrier frequency and gives us the baseband signal that we wanted. Just as in transmitters, it's normal to do this in two stages. An expensive stage with expensive components like oscillators and multipliers that gets us down to an intermediate frequency, but can use low-pass filters at the intermediate frequency, so this is much cheaper than filtering at the input. And then possibly a tunable second stage so that we can move between different channels in our communications band. The other reasons about expense and stability of these oscillators also remain. So typically, we could have a bandpass filter here at the intermediate frequency that allows us to select the channel that we wish. So this is the hardware layout you're likely to have in your radio receiver at home. So non-coherent detector. Those two methods, the super heterodyne method, relied on having oscillators locked to the oscillations at the transmitter. But the envelope detector doesn't need any local oscillator. It demodulates in much the same way you would with a felt tip pen, of just joining the peaks in the amplitude modulated signal it receives. So here we have a circuit that attempts to achieve that. It has a non-linear element, as it needs to move between different frequencies. This is called an envelope detector. It has an input UI, which will be the modulated signal, and an output UO, which approximates this red line of joining the peaks of our signal. In the next slide we see how this system works. Here we have our envelope detection circuit again. It operates in two different states depending whether UI, the input voltage, is higher or lower than UO, the output voltage. When UI is bigger than UO, we have the fast charge state. In that case, this diode is forward biased, and so it looks like a small resistor. If we have a voltage UI bigger than UOut, then that leads to a current flowing through this resistor, and it charges this capacitor. And the effect is that UOut will grow as the capacitor charges to follow UI. When UI drops below UOut, then this diode is reverse biased, and it acts like an open switch, so this part of the circuit is not there at all. In that case, the capacitor discharges through the resistor, and the output voltage UO decays exponentially with a time constant given by the capacitance and the resistance. So this is the time constant of discharging. So these graphs illustrate how the output of a envelope detector tracks that of a signal. For all of them, in the leading edge where the modulated signal is increasing, then the output of the envelope detector tracks it. But when the input drops again, then the envelope detector switches to the other mode and slowly discharges. So although these look like straight lines, they're the beginnings of an exponential decline. So this is where you choose the time constant of the resistor and capacitor to be about right. If it's too large, then the decay isn't fast enough to track the amplitude as it gets smaller, and you'll distort your signal. If this time constant is too small, then the decay is too fast and you don't do much demodulation. You see that there's still a high frequency component at the carrier frequency here. So we have these two heuristics. Firstly, the charging time constant must be much smaller than the carrier frequency. This is so you can track increasing signal. And the second time constant, for the discharge time constant, has to be between the message signal frequency and that of the carrier. Envelope detectors are often mixed with super heterodyne demodulation. So you can have the expensive part that gets you down from the carrier frequency to the intermediate frequency, and then use an envelope detection after that. So in summary, changing frequency always requires a nonlinear device. Super heterodyne modulation and demodulation works by multiplication of our signal by the sinusoid produced by a local oscillator, generally followed by the filtering out of either the sum or difference frequency, depending if it's a transmitter or receiver. Super heterodyne demodulation often occurs in several stages, and there are several reasons for this. Cheaper, allows you to tune to different channels and to combine signals from different channels using relatively inexpensive hardware at the intermediate frequency. Non-coherent envelope detection can also be combined with super heterodyne demodulation to form a receiver.